All right, we're going to go ahead and take a look at the homework for 4.5. So these are optimization problems. First problem, it says consider the following problem. Find two numbers whose sum is 23 and whose product is a maximum. So they want us in this first part to just complete filling out this table. So if our first number is 1, then our second number has to be 22 because they have to add up to be 23. We multiply those two together, we get a product of 22. If we let our first number be 2, then our second number needs to be 21 so that they add up to be the 23 again. And when we multiply those, we get 42. I can keep on doing this, trying to figure out what's going to happen. So if I let the first number be 3, then the second number has to be 20. And multiply those together, we get 60. So it looks like the products are getting bigger and bigger as we go. Let me try 4. If this is 4, then this has to be 19. If we multiply those together, I may as well get my calculator out here because I'll probably need it. All right. Oh, man. All right, so we get 76. So again, it appears that they're getting larger. If our first number is 5, then our second number has to be 18. We do 5 times 18, and we get that 90. So again, they look like they're getting bigger and bigger. 6, this has to be 17. We get 102, 7, and 16 is 112. So maybe there is no combination that these just keep getting bigger and bigger and it doesn't matter, but we'll see here what's going to happen. 8 and 15, multiply those together, we get 120. And then 9 and 14, we get 126. 10 and 13, 130. 11 and 12, we get 132. So it looks like the maximum that we would get is if we do this one right here. If we let one numbers be 11, the other one be 12, we get 132. Because if we keep on going with this table, the next number would be 12, but then the other number would be 11. We've already done that. So it looks like that's our best answer. Smallest number 11, largest one is 12. However, this is not correct. There are some other numbers that will get us even bigger number, but they're not easy numbers for us to just look at visually and identify. So we're going to use calculus now. So here's what we need. We have two numbers, x and y. We need them to add up to be 23. So this is our what we call constraint equation. Okay, we have to have those two numbers add up to be 23. But on the other hand, we want to try and find the maximum product, so the largest number we can get when we multiply them. So P is the thing I'm trying to find the maximum of, the maximum product. And so we're trying to optimize this function. To do this, what we're going to have to do is look at this equation, and we're going to have to rewrite it so that we only have one variable. Right now we have two variables, x and y. So what I'm going to do is replace this y with something. But we know that y has to satisfy this equation up here. So if I take that y and I solve for y here, I get 23 minus x. Now if I bring that down here and rewrite this equation for p, we get x times 23 minus x. And now if I distribute through, I get 23x minus x squared. Now all you have to do is give me x, which would be one of the numbers, right? We could have called, like over here, our first number is x, our second number is y. You give me just one of those numbers, and I should be able to tell you what the product is. Now, since I can do that, my p is now a function of one variable, so I say p is a function of x. And now what we're doing is, that was a notice that my headset, I don't know if you saw that, my headset battery is getting ready to die. It's not a good thing. So now what I need to do is try and find the maximum of this. Now, what I do know is that x has to be bigger than 0. because we won't even look at the negative numbers here, because we need to, well, I suppose we could have two negative numbers, so we should look at that. So let's not even restrict our domain. So how do we find maximum minimums of a function? So the way we do it, first thing, take derivative through this is 23 minus 2x. And then we set that equal to 0. So the derivative equal to 0 means I set 23 minus 2x equal to 0. I solve for x. When I solve for x, I get that x is, come back up here, x is 23 divided by 2. So to prove that that's a maximum, that that's where I'm going to have a maximum, that p will have a max, what I do is I take my number line, I put my critical number here, 23 over 2, splits up my number line, and now I pick some test points. So I pick something to the left, pick something to the right of that. Now 23 divided by 2 is 11.5, so I can pick anything to the left of this, so how about I pick 1? Anything to the right of that, so how about I pick 20? And what I'm going to do is I'm going to plug those values into the derivative, so I'm going to plug them in right here. What I'm looking for is, positive and negative will tell me if I'm increasing or decreasing. So if I plug 1 in here, so take 1, plug 1 right in there, you get 23 minus 2. That's going to be 21. That's a positive number, which means my original function p is going up here. And then if I plug in 20, you get 23 minus 40. That's a negative number, so that tells me that my p is going down here. So that means this original product function goes up and then goes down at this 23 over 2, which means that 23 over 2 is a maximum. So if I let x be equal to 23 over 2, I should be able to get y now. So I go back over to the equation over here on the right for y, and I plug in what x is. So that means that y is equal to 23 minus 23 over 2. Those are my dogs that just won't be quiet. I should say my wife's dogs. 46 over 2 minus 23 over 2. So I get a common denominator there. So y is also equal to, if you subtract there, you get 23 over 2 again. So that tells me that my x and y are going to be the same number. So to answer the question, if my smallest number is 23 over 2, my largest is 23 over 2, and of course they're the same number. Now, if we take those two numbers and add them together, let's just check that this works. If we add those two numbers together, 23 over 2 plus 23 over 2, I should get 23. So of course you add this together, you get 46 over 2. And that is 23, so that checks. But now if I multiply them, 23 over 2 times 23 over 2, I get, let's see, 23 multiplying straight across, get 529 over 4. So that gives me 132.25. So as you can see, 132.25 is a little bit bigger than the 132 here. In fact, 132.5 is the maximum product that I could ever get with these conditions. So even though the table was pretty good at giving us an idea, the calculus gives us the exact answer. All right, moving along. Find the dimensions of a rectangle with a perimeter of 100 whose area is large as possible. So let me start with a picture. I have a rectangle. Rectangle has, I'll say, x and y. And what I know is that the perimeter is 100 meters. Now the perimeter is a total distance around. So total distance around this thing is an x plus a y plus another x plus another y. So my perimeter is going to be 2x plus 2y must be 100. And just to make this equation easier to work with, I'm just going to divide everything by 2. So now this is my new constraint equation. Now let me go try and figure out what it is that I'm trying to find the maximum of. I'm trying to find the largest area possible. So let me write the equation for area. The area of this rectangle is x times y. Now again, my area depends on two variables, x and y, so I'm going to try and rewrite it so it has only one variable. So I'm going to try and replace my y here. So I'm going to go to this equation over here, my constraint. I'm going to solve it for y. If I solve that for y, y is equal to 50 minus x. And now I'm going to plug that in over here for y. So I get 50 minus x here. oops, 50 minus x. And now this means that my area is 50x minus x squared. And I can now say that my area is completely a function of x, and that equals 50x minus x squared. Now, I should talk a little bit about domain here. It is possible that it is not possible for us to have a rectangle if x is a negative number. So I'm going to say that x must be greater than or equal to 0. So I'm only going to be looking on the positive side, or the right side of the number line for answers here. So the way we figure out where this function, this area function, will have a maximum is to, again, take its derivative, figure out where it's 0. We also want to look at where it's undefined, but we're not going to have to worry about that because it's a polynomial. So let's take our derivative. The derivative, actually, we want the derivative set it equal to 0, so I'm going to do it all at one step here. Derivative of a is 50 minus 2x. I want to set that equal to 0. Solve for x. I get x is 50 over 2. Then I draw a number line, 50 over 2. All right, oh, 25. I should just write 25, huh? Let me just erase that, 25. That breaks up my number line. I'm going to pick test point here and here, plug those into the derivative. So how about 1? I like 1. And how about 30? Plug those into the derivative. So I'm plugging those into my derivatives right here. And forget that that 0 is there for right now, because all I'm doing is evaluating the derivative at those 2 points. If I plug in 1, get 50 minus 2, it's a positive number, so I know that my area function goes up here. And then plug in 30, we get a negative number, so area goes down. That means that I get a maximum when I let x be equal to 25. So if I let x be 25, then I can solve for y using that equation. That means y is 25. So what that tells me is that if you're going to draw a rectangle that has that you want to have a perimeter of 100 meters on, then to get the maximum area, you actually need to make your rectangle be a square. So 25, 25, we're done. I really don't know how much time I'm going to have with my headset, so it might just die, and if it does, I'll have to stop the video. Okay, find the dimensions of a rectangle with area of 343 meters squared whose perimeter is as small as possible. This problem is like opposite of what we just did. I'm given in this problem the constraint that the rectangle has an area of 343 square meters. So I have a rectangle, x, y. I'm told that the area is 343. Well, the area is x times y, so I know that x times y is 343. So that's my constraint. Now, what is it that I'm trying to find the maximum or minimum of? In this problem, it's minimum. I want to find the perimeter is, when the perimeter is as small as possible. So I need to write down what the perimeter equation is. The perimeter of this, we already know, was 2x plus 2y. And I need to get this all in terms of one variable. So I'm going to replace my y in the problem with whatever this equation gives me. So I need to solve this equation for y. Let me do that. Y is equal to 343 divided by x. So I divide both sides by x. And I take that and I plug it in over here for y. So my perimeter is 2x plus 2 times 343 over x. And now what I'm going to do is I'm going to clean that up over here. And my perimeter is now a function of one variable. So I got 2x plus, I can just multiply that 2 straight across. So 2 times 343 gives me 686 over x. Now I'm going to need to take the derivative of that. I should also mention that x here has to be strictly bigger than 0. It can't be 0 because if x is 0, then I would have undefined right here. So x has to be a positive number. So because I know I need to take the derivative, let me just rewrite it first so it'll be easier to take derivative. What I'm going to do is I'm going to bring this x that's on the bottom up. So 686 x to the negative 1, and that way I can just do the power rule. So my derivative is equal to 2 minus, so I'm bringing that power up front, remember, 686 x to the negative 2. Subtract 1 from the power. And what I need to do now is I need to set that equal to 0. So let me rewrite it again so that you can work with it a little better. That's our derivative. I want to know when it's equal to 0. Little dog has a barking problem. Set that equal to 0. So the way I'm going to solve that is I am going to move this entire term to the other side, which makes it positive. 2 equals 686 over x squared. I'm going to multiply both sides by x squared. These cancel on the right side. Left side I have x squared times 2. I'll divide the 2 on both sides. That'll give me 343. And then I take the square root. So I take the square root of 343, and that's not a nice number. You get, well, I'm just going to say square root of 343. We might have to simplify that later, but that's what it is. And as a decimal, it's about 18.52. So it's approximately 18.52. Now what I need to do is make sure that this is where we had a smallest possible value. So the only way to check that that's true is to take a look at the number line, break it up, and test some points. So be careful, because when you do this on a test for the final, if you just get this answer and you never check to show that it's a max or a min, depending on the problem, you'll get points taken off. So I have to verify that this is actually a minimum point. So I break up my number line. I pick any number over here, but remember I have to be bigger than 0. So how about 1? And over here, let's go for 20. What I'm going to do is I'm going to plug those into the derivative. Remember, the derivative was 2 minus 686 over x squared. That was my derivative. So when I plug in 1, what happens here? Plug in 1, 686 divided by 1 is just 686. 2 minus 686, that's a negative number. That means my perimeter function is going down here. When I plug in 20, if you do 686 divided by 20 squared, right? And I'm going to get that as a decimal. It's going to be 1.75. So 2 minus 1.75 is a positive number. So that means my perimeter function is going up, which means I do have a minimum value at 18.52, or square root of 343. Now that's just what x is. I also need to find what y is. So if we go back, remember we said that y was equal to 343 divided by x. That means y is 343 divided by the square root of 343, and I'm almost sure the book's not, or the computer wants you to rationalize this, so I'm going to multiply top and bottom by root 343. And what happens is on the bottom, you multiply these two together, you get 343, and then that 343 on the top cancels with those, and then all you're left with is square root 343. So your y is 343. All right, notice root 343. So notice your x and y's are the same value. It's not always going to work out that way. It's just these examples to start off are kind of basic. So your answers often turn out to be the same. All right, let me see. Make sure. Let's see how much they show you here. Well, okay. Do they ask for find the dimensions? Okay, so they only want the dimensions. They don't ask for the actual perimeter. But if you wanted to get the perimeter, you could, because you could just go 2 times this plus 2 times that, which is basically 4 of these. But it's not asked for in the problem. All right, move along. I'm worried about my battery running out here. Consider the following problem. A box with an open top is to be constructed from a square piece of cardboard 3 foot wide by cutting out square from each corner of the 4 corners and bending its sides up. Find the largest possible volume such box can have. All right, so let me draw this on a different page. We have a square piece of cardboard. It's my best square I can get there. Then it's 3 feet. Is it 3 feet? It's 3 feet wide, so it's square, so 3 feet by 3 feet. What we're going to do is we're going to come in here and we're going to cut out the corners. So whatever we cut out of the one corner, we have to cut out all corners. Once that's cut out, we're going to fold it along this line, this line, this line, this line. When we fold the sides up, we will get something like this. I'm not asking you to be an artist here, but this will just give you a better idea of what's happening. Okay, so that's what happened. We folded things up. Now, to do this problem, what we'll do is we'll say that the amount that we cut out, okay, so the width of this cut is something we don't know. It's x. And that means that this is also x. And same thing for each corner, x, 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 x. So when we fold up the sides, let's take a look at this edge right here. How long is this edge? And that corresponds to this edge of this. Well, that length is the total 3 feet it was, but then we took off x and took off x there, which means that this piece is 3, take away 2 of those x's. Okay, that's what this distance is right in here. And the same thing goes for this edge. This edge was also 3. And then we took away the 2 x's there. So take away 2x, that represents just this piece. Now the reason I'm doing this is because I'm trying to find, going back to the question here, trying to find the largest volume that this box can possibly have. So depending on the size of this x, I could have different shaped boxes. You know, if I make a real big cut, then my box would be very tall, but not as wide. So just by varying that cut, it changes the dimensions. So we're trying to find the maximum volume here. And volume, of course, if this is my box, if this is length and width and height, volume is always length times width times height. For us, the length and the width are the same. This is your length, this is your width. Okay? You can say that's this and that's that. So what we have is 3 minus 2x times 3 minus 2x, that's length times width, and then times height. Now notice that when we fold up that edge, this right here corresponds to these 2 sides right there. So that is our x because that got folded up. So this piece right here is x. So that means the height is x. So I put an x here. And now what I'll do is I'll notice my volume here can be distributed, right? I'm going to get this is all a function of x. I'm going to do a little foiling here. And I would get my volume is now a function of x. It is 9, let's see, minus 6x, and then minus another 6x and minus 12x. Then we have plus 4x squared, then all times x. Distribute that last x through, and I'll put it in descending order. 4x cubed minus 12x squared plus 9x. This is my volume function, my x. My x is actually bounded. The smallest the x can be is 0, because then it wouldn't make sense. We wouldn't have anything. The biggest the x can be is a little tricky because this x is this side, but it's also this side, so you could only meet in the middle. So the largest it could be here would be the 3 over 2, and then this side 3 over 2. So x is between 0 and 3 over 2. And so what I'll do now is I'll take my derivative. Derivative of this is 12x squared minus 24x plus 9. Now I'm now going to set my derivative equal to 0. And that means I'm going to take 12x squared minus 24x plus 9. Set it equal to 0. Let's see, I can divide through by a factor of 3. So we get 4x squared minus 8x plus 3 equals 0. This is a quadratic equation. So there's different ways to solve this. You could probably use quadratic formula. You could try factoring. I don't think, will factoring work? 12, yeah, that will work, I believe. Let's see, let's try this. 2x, 3, and 1, negative and negative. See what happens here. If we multiply that, it's 4x squared minus 6x minus 2x, that's minus 8x, and then the last two multiply. So that's it. Now you could also use quadratic formula and you get to the same answers, but we set each of these equal to 0. You get x is 1/2. You get x is 3/2. And so now what I'm going to do is just notice that x is 3/2 actually is one of my endpoints, and x is 1/2 is in there somewhere. So there's two ways to approach this. I can look at this as if it's on a closed interval, or I can do the open interval method where I just do a number line. I think I'm just going to do a number line real quick to check that at 1/2 is where I have the maximum. So if I plug in some points, so if I plug in, let's say 1/4, plug in something bigger, but I can't be bigger than 3/2, so how about, like, I don't know, 0.6. I plug those into the derivative, so plug them into here. So that might be a little bit tedious, so why don't instead we plug them in here. Forget that that's a 0, just plug them in. So if I take this and I plug in 1/4, so 2 times 1/4 minus 3, what would I get here? Well, 2 times the 4th is a 1/2. 1/2 minus 1 is a negative number. Times over here, 2 times the 4th is a 1/2. Times the negative number, you get another negative. Negative and negative multiply to be positive. That means that my volume function is going up here. And if I plug in 0.6, same way, 2 times 0.6 minus 1 times 2 times 0.6 minus 3. We're hoping for a negative number here. So 2 times 0.6 is 1.2. Subtract 1, that's positive. 2 times 0.6 is 1.2 times, or minus 3 is negative. Positive times negative is negative. That means our volume goes down here. That means we have a maximum here. And so if x is equal to 1/2, we should get a maximum volume. Now, does the problem ask for the actual maximum volume? Let's see. Write the volume as a function of x. They do this. They ask for some stuff a little bit different. Write the expression of volume in terms of x and y. And I'll let you kind of, I'll look at the solution for you. That's not important. What's important to me is you getting to these last two answers. Finish solving the problem by finding the largest volume. So yes, they do want the volume. So remember that the volume was actually x times y times z. I'm sorry, length times width times height. So this is our volume equation right here. All we have to do is plug in 1/2 for x into the whole thing. So I think I'll do it right here. Our maximum volume, volume max, will happen when x is 1/2. So plug 1/2 in right here. 1/2 of 2 is 1. So we get 3 minus 1, that's 2, times, now we already know 1/2 of 2 is 1, 3 minus 1 is 2, times, and then over here we plug in 1/2. So you get 2 times 2 is 4, 1/2 of that, that's 2. And was the measurement in feet? Yes, it was. So 2 cubic feet is the maximum volume that you're going to get. I will take a look at their answer so you can maybe see those parts for the intermediate steps. Wonder if they're going to give you a picture. Yeah, they kind of give you a picture. Now, they call this piece y instead. Okay, so here it is. Let you take a look at that, but you see we get the same thing. They do a closed interval method, so all they did was they checked the endpoints. They plugged the endpoints into the original function, not the derivative, and then they also plugged in the critical number, which was 1/2, into the original function and got 2. So using closed interval method versus open, kind of your choice there. See how many problems I've got left here. One more? Two more. All right. I don't think, I'm really skeptical if my battery's going to last this long, but I'm going to go for it. Find the point on the line y equals 3x plus 4 that is closest to the origin. You know, I think I'm going to work through their solution here. You think that's going to work? Let me see. Okay. The distance d from the origin, which is this point, to a point, now let me explain what this point is. Since y is always this coordinate, I can replace the y with that equation. So I just heard something weird on my headset. It's still going. Let me make sure it's coming out on my video. Yeah, my audio is still there. Okay, so what we had is we had the origin, and then we have a line here. This line is somewhere up here, like that. We're trying to find the point on that line that's closest to the origin. So it's obviously not here, and it's not here. It's somewhere, but any point on that line can be written xy. But because they give us the equation on the line, it's written x, 3x plus 4. Now, the distance between 2 points, so these are 2 arbitrary points. Well, not arbitrary. 0, 0 is not arbitrary, but we have 0, 0, and then we have an arbitrary point on that line. The distance between any 2 points you can find, go back into your college algebra book or something, look it up on Google. Distance between 2 points, if this is x1, y1, x2, y2, distance between 2 points is square root of x2 minus x1 squared plus y2 minus y1 squared, or there's other variations, but that's basically it. So I'm taking, I do that, plug in, I get this. X minus 0 squared is just x, and then this right here is 3x plus 4 squared. Now, whenever we have a problem like this, trying to figure out minimum or maximum distances, it's always easier to, instead of looking at d, look at d squared. And the reason why is because it gets rid of the square root. So if I square the d, we'll call it s, then the square root goes away, and then you get this. So we want to know when that is the smallest it can possibly be. So all we do is take the derivative, which is here, and then we simplify that derivative. We set that derivative equal to 0, which means that when you solve this equation set equal to 0, you get negative 6/5. And then now the way they're doing is they're going to do a second derivative test, which is fine. Second derivative test will tell us if this is a max or min. So once we have x is negative 6/5, we're going to take the second derivative. Second derivative of that is 20. Since that is a positive number, what we have is that for this s function, at negative 6/5, our derivative is 0, which means the slope of the tangent line is flat. But then our second derivative is positive, which means second derivative is our concavity, which means that we're concave up there, which means at that point must be the lowest point on the graph, which means it's a minimum. And then, so once we conclude it's a minimum, we can take that point, figure out what y is. To figure out what y is, just take that x value, negative 6/5, plug it into the x right there and compute that. And that's your 2/5. Now, just for the sake of being clear here, you could have, again, done a number line. You could have said negative 6/5. You could have tested points. If you like that method, you would have shown that to the left it's going down, to the right it's going up. Your s function is going down, s function is going up, which means that you had a minimum value there. All right, a Norman window. Due to time constraints on my battery life, I'm going to show you the answer to this. I believe I worked through one of these in class in one of the videos. So this is what a Norman window looks like. So you draw a rectangle, and then you make a circle up here, which means that this distance is half of the distance all the way across, right? This is like the diameter of the circle, so half of that's the radius. So the main thing is just trying to come up with a formula for the area of this. So the area of that is x times y, which is, what do they want to find? Maximum area, here we go. So the area here is x times y, and then plus the area of this half circle. So remember, the area of a circle is pi r squared. The radius of this is this. So pi r squared would be pi times x squared over 4. So pi times x squared over 4 is what you can get here. But remember, that's the area of a whole circle. We want to cut it in half, so you put a half in front of that. So what we do is we try and find the maximum of this. So the problem here is that we have a y. So to get y, we had to go back to the constraint. And the constraint was that the perimeter of the window had to be equal to 30. Now, perimeter of this window is x plus y plus another y, so x plus 2y. That's this part right here. And then, remember, the perimeter of a circle is the same as circumference. And the circumference of a circle is 2 pi r, but we're only going halfway around, so it's just going to be pi times r. So this is pi times r. So that equation right there is our constraint equation, and you can solve it for y like this, moving things around. And then once you get that y, you take that y and you plug it into this area function, and then that goes right here. And then you have that part right here, which came from this. And now that's the thing that you're going to take the derivative of. And then from there, you can go ahead and either use the second derivative test or, again, break up that number line. See how you do with that. That's it for now. I won't be able to post another video for a while until I get my batteries charged on my headset.